If you've ever seen a surface map before, you've seen a bunch of these different symbols and numbers. All across the US and really all across the world are a bunch of weather recording stations. These are made up of instruments that record a bunch of different types of atmospheric variables: temperature, pressure, wind speed and direction, dew point, etc. Now, displaying all of this data on a single map is quite cumbersome. It's pretty difficult. So we had to come up with a way to more neatly display all of this data without it being just a total mess. And that is done through the use of station plots. Each one of these symbols and the corresponding numbers around it indicate data from a single weather station. The problem is that a lot of this data is in code so that it can be truncated down to take up less space on the map. What we're going to do is help you decode that data, let you know which numbers are which, and show you what all the symbols mean. This is what a typical station plot looks like, and there's a lot of stuff on here. It's pretty busy, and there can actually be more stuff on here, including symbols for present and past weather, but those are very rarely included in any surface map source that you will use. And actually, most of the time you won't see even this much stuff on a station plot, but usually there will be some combination of these things on a station plot you'll see, depending on the source that you use. The most critical things that you'll most often see on a station plot, aside from the staff symbol here, which we'll talk about in just a bit, are these four right here. Starting with the value at the top left, that is the surface temperature in degrees Fahrenheit. The value on the bottom left is the surface dew point in degrees Fahrenheit. So at this particular station, the surface temperature is 77 degrees Fahrenheit with a dew point of 58 degrees Fahrenheit. The value at the top right of the station plot is the surface pressure at the station, given in units of millibars. Now, to conserve some space, this value is given in code. Either the leading 9 or 10 of the actual pressure value has been lopped off. So how do we know which is the case? Well, if the leading digit of the value listed on the station plot is a value from 0 to 4, the leading 10 has been lopped off. Whereas if the leading digit is from 5 to 9, the leading 9 has been lopped off. So in this case, our leading digit is a 0, so we know the leading 10 has been lopped off. We then put a decimal point between the last two digits to get our final pressure value of 1001.2 millibars. Let's say this was 912 instead of 012. In that case, the leading digit is between 5 and 9, so we know the leading 9 would have been chopped off for a final pressure of 991.2 millibars. And these three letters at the bottom right of the station plot are your station identifier. In this example, LBB stands for Lubbock, Texas. If the station is at an airport, it will share the airport code, but it just basically tells you which station you're looking at. These four things are the ones that you'll almost always see, aside from the staff that you see there, again, because we can't do a successful surface analysis without looking at how things like temperature, moisture, and pressure change across a given area.
The Chaser Academy is our premium subscription, and it's the best deal in storm chasing. Link in the description.
But there are some other things that are sometimes listed on station plots, so let's go through those, starting with this one here on the far left. This is the visibility at the recording station at the time of observation, given in units of miles. And this is not written in code. It can be given in fractional numbers. For example, you see here, 3/4 means that visibility is 3/4 of a mile. If it were to be a number like 5, that would mean a visibility of 5 miles. Or for example, 2.5, that would mean a visibility of 2.5 miles at the time of observation. Let's move on to this symbol that's right next to the visibility value. This is the present weather symbol. Essentially, it is the weather that is observed either at the time of or in the past hour before the observation was taken. Now, there are a bunch of different present weather symbols, almost 100 in fact. The most common ones you might often see are visibility reduced by smoke or haze, rain or drizzle, snow, or thunderstorms of different hazards and intensities. In our example here, we see this R-shaped symbol. So we go to our chart and we figure out that this represents thunder heard at the station at the time of observation, not associated with any precipitation at the station. So in other words, a nearby thunderstorm. Moving over to the opposite side of the station plot, we find this number and the corresponding symbol. These represent the pressure tendency at the station over the past 3 hours. So in essence, how much the pressure has changed at the station in the 3 hours leading up to the observation. The number you see there quantifies the change in pressure in millibars over the past 3 hours. If the value is positive, that means the pressure has overall risen. And if the value is negative, that means the pressure has fallen. And this number is written in code. The decimal point has been dropped, so we just reinsert the decimal point between the two digits. So in this case, we see a negative 23. That means because it's negative, the pressure has fallen. And we put the decimal point in between the two digits, meaning that the pressure has fallen 2.3 millibars in the past 3 hours. The corresponding symbol you see next to the pressure change value gives us more of a qualitative look at how the pressure has changed over the past 3 hours. Here is a chart of all of the pressure tendency symbols you might see. If the line slopes downward from left to right, that indicates the pressure was falling. If the line slopes upward from left to right, that indicates the pressure was rising. And if the line is flat, that means the pressure was steady. And we can have a combination of all of these. For example, this one here. Initially the pressure was falling, but then it leveled off. And this one here, for instance, the pressure was falling before it started to rise toward the end of that 3-hour period. In our example here, you can see that the line is only sloping downward from left to right, which means that the pressure was continuously falling over that previous 3-hour period. All right, now let's look at the central circle and the staff-looking thing that is extending from it. We'll start off with the central circle. This denotes the actual location of the station, but how much it's filled in represents how much cloud cover there is in the sky. And the way we do this is by using Oktas. Basically, we split the sky up into eighths, and 1 octa is 1/8 of the sky that's covered. You can see that an open circle means that the sky is clear, there are no clouds in the sky, and a full circle means that all 8 of those octas are covered by clouds, meaning that the sky is completely overcast. If the central circle is only half filled in, that means that 4 out of the 8 octas, or 1/2 of the octas, are covered, meaning that half the sky is covered by clouds, and we have everything in between. For example, if 2 of those octas are filled in, that means 1/4 or 1/4 of the sky is covered. And if 6 out of the 8 octas are covered, meaning 3/4 of the sky is covered by clouds, the symbol looks like this. In our example here, the circle is fully filled in, meaning that the sky is completely overcast. All right, let's now talk about the staff or key-looking thing emanating from the central circle. This is the wind barb, and it tells us the wind speed and direction at the station at the time of observation. Let's start with wind direction. First, we have to know how wind is categorized in meteorology. Wind is described by where it's coming from, not where it's going to. So for example, if wind is blowing from the south toward the north, that is considered a southerly wind because the wind is coming from the south. If the wind is blowing from the east toward the west, that is considered an easterly wind, and so on and so forth. On a station plot, the wind direction can be found by drawing an arrow through the flags at the end of the wind barb toward the center of the station. So in this case, this would be a northeasterly wind because the wind is coming from the northeast toward the southwest. As for wind speed, that is determined by the number of flags on the end of the wind barb. And there are 3 types of these flags or barbs or staffs or whatever you want to call them that you might encounter when looking at station plots. This triangle shape you see here that looks like an actual flag, this full barb, and then the half barb. Each of these represent a different value of wind speed in knots. The half barb is equal to 5 knots, the full barb is equal to 10 knots, and the flag here is equal to 50 knots. And the way to calculate the wind speed is to simply add up the corresponding values of each staff or flag on the wind barb. So in this case here, we have a 50 knot flag plus a full barb, which is 10 knots, plus a half barb, which is 5 knots. 50 plus 10 plus 5 equals 65 knots. That would be our wind speed at this particular location. How about this one? Well, we have 3 full barbs, so we have 10 knots plus 10 knots plus 10 knots, which equals 30 knots. And how about this one? We have a half barb, which is 5, 2 full barbs, which are 10 knots each, and then we have 2 flags. Those are 50 knots each. So we just add those up. 50 plus 50 is 100, plus 10 is 110, plus another 10 is 120, plus 5 is 125 knots. Going back to our example station plot, we see we have 2 full barbs, 10 knots each, plus a half barb of 5 knots. 10 plus 10 plus 5 is 25 knots. So the wind at this station is northeasterly at 25 knots. Now, sometimes you might see something like this, where we don't have a wind barb, but we have 2 concentric circles. The inner circle is the cloud cover information like we talked about earlier, but the outer circle, without a wind barb, tells you that the winds are calm at that station. And then for this final value here, this G39, that is the maximum wind gust recorded at the station in units of knots. So in this case, the maximum gust at the station has been 39 knots. And there you have it. That is how to decipher most of the values that you might see on a surface station plot. Now that we know the basics, let's run through another full example. So this is a station plot from Flagstaff. I'll let you know that FLG stands for Flagstaff, Arizona. Let's start up here with the temperature at the top left. Our temperature is 31 degrees Fahrenheit with a dew point of 29 degrees Fahrenheit. Let's now figure out our pressure at the station. We first take a look at that first digit. We see that it's between 5 and 9, so we know the leading 9 has been lopped off. We then put a decimal point between the last 2 digits for a final pressure of 989.6 millibars. And we know that the pressure is falling or has fallen in the past 3 hours. This value here is negative. We put a decimal point between the 2 digits there. So we know the pressure has overall fallen a half millibar in the past 3 hours. And we can see that at first the pressure was rising, given the upward sloping line there, before a greater fall up to the point of observation. The visibility, as we see here, is 2 miles. And for our present weather, let's go to our chart. We can see that it is 2 of those asterisk symbols. So we go ahead and find that on the chart, and we see that it is this one here. The continuous fall of snowflakes with slight snowfall at the time of observation. Our central circle is completely filled in, so we have complete overcast skies at Flagstaff at the time of observation. And finally, let's figure out our wind speed and direction. So for our wind direction, we draw an arrow through the flags toward the station, so we know the wind is southerly, coming from the south to the north. And we see we have 3 full barbs here. Those are 10 knots each. So 10 plus 10 plus 10, that equals 30 knots. So our wind at Flagstaff at the time of observation is a southerly wind at 30 knots, with gusts to 51 knots. All right, let's now take a look at the symbols for different boundaries, such as frontal zones, that you'll see on surface maps. Again, we're going to show you how to actually analyze frontal zones in our next episode when we show you how to do a full surface analysis. But I just want to get you acclimated to the different symbols that you might see on a surface map. Let's start off with pressure systems, low pressure and high pressure. Frontal zones are tied to low pressure systems, so determining where pressure systems are on a surface map is quite important. The center of a low pressure system is indicated by a red L, whereas the center of a high pressure system is indicated by a blue H. Moving on to boundaries, let's start with a cold front. A cold front is the boundary between a colder air mass that's moving into a region of warmer air. A cold front is denoted by a blue line with blue triangles. On the other hand, a warm front is the boundary between a region of warmer air moving into a region of cooler air, and it's denoted by a red line with red semicircles. A stationary front is the boundary between 2 air masses of different temperature characteristics, but neither is moving into the other. In essence, the boundary is not moving, so it's stationary. In this case, we use an alternating red and blue line with corresponding red semicircles and blue triangles. An occluded front is when the cold front of a mid-latitude cyclone or low pressure system catches up to and displaces the warm front off the surface. This is denoted by a purple line with alternating purple triangles and semicircles. A dry line is the boundary between hot, dry air to the west and warm, moist air to the east, and it's a critical feature of many severe weather setups in the plains especially. Dry lines are denoted by brown lines with brown semicircles that are not filled in.
The Chaser Academy is our premium subscription on Discord, and it is without a doubt the best deal in storm chasing. For less than the cost of a combo meal at McDonald's, you'll unlock instant access to 24/7 text-based Q&A with our expert coaches, weekly group coaching sessions featuring live Q&A, and on-demand replays after each session has completed. Plans start as low as $7.20 per month, so subscribe now and take advantage of the best deal in storm chasing. Link in the description.
We can also analyze the locations of ongoing squall lines on a surface map, and those are denoted by these alternating dashes and pairs of dots, colored in red. If you are analyzing a squall line on a surface map, this symbol is placed at the leading edge of the band of thunderstorms. And finally, surface troughs can be identified on surface maps. A surface trough is basically an elongated area of slightly lower pressures than its surroundings. It perhaps doesn't have the temperature gradient needed to be a full-fledged frontal zone, and it may not even be connected with a mid-latitude cyclone or low pressure system, but surface troughs are notable because they may have the ability to initiate thunderstorms. Surface troughs are denoted by a dashed brown line. Now, one thing to keep in mind with these symbols, the pips, the triangles of a cold front, the semicircles of a warm front, etc., are always placed in the direction of movement of the front. So for example, if we have a cold front that looks like this and our triangles are facing toward the right, we know that the cold front is moving toward the right, with cold air moving into a region of warmer air. Same thing with a warm front. Let's say our semicircles are oriented upward. That would mean that warm air is to the south, moving into a region of colder air, so our front is moving from south to north. In the case of a stationary front, the pips are always facing away from their corresponding air mass. So in this example here, the blue triangles, which typically represent a cold front, cold air moving into warm air, are facing this way, which means that cold air would be to the north of the boundary and warm air to the south. This makes sense with our red semicircles, which are associated with a warm front typically, warm air moving into cold air. They are facing from the warm air into the area of colder air. Here's an example of what some of these symbols look like on an actual surface map. We have a surface low located in northern Colorado, as indicated by the red L there. The cold front draped down to the south. You see the blue line with the blue triangles. The triangles are facing to the right, so cold air is located to the west of the front, warm air is located to the east. And we do notice that a portion of our warm front, which is indicated by the red line with the semicircles, has been overtaken by the cold front, leading to a portion of the front that has been occluded, and you can see that in the purple segment right there near the surface low. We also have a bit of a stationary front out here, the eastern extent of that warm front, and a dry line extending south from Kansas into West Texas.
Remember to check out those links in the description below, and then watch another video.